The origin for the nanoscale to differ from the macroscale is found in the finite discretization of matter, namely the atom, and its integrations and agglomeration into sophisticated structures. Hence I will start our discussion on what makes Nano tick by providing a brief historical reprise on what was involved in bringing the atom to life. Let's go back to the ancient Greeks around 500 BC, where logical thinking brought forward the idea of the atom. Logic-based arguments built on a two-element universe consisting of matter and vacuum let Leucippus and Democritus postulate atoms as the ultimate, not further dividable building blocks. In particular, intriguing with this hypothesis were the follow-ups, that is, the arguments used to explain the material's states and the many properties. It was argued they arise from the shape and weight of the atoms. For instance, water atoms were conceived smooth and slippery, giving water a liquid behavior, while iron atoms were considered to be interlocked, giving the material the solid strength. As we will see in the next slide, it took mankind another 2 millennia to accept this original idea of matter being composed of atomic molecular building blocks. The progress from the 1700 to the 1900 towards an atomistic theory is here put in perspective with the historical development of the three other branches of physics, namely the theory of heat, electrodynamics, and mechanics. Important preludes to the atomic theory were Boyle's first supporting experimental evidence underpinning the atomic hypothesis, Bernoulli and Euler's original particle theory for gases based on Boyle's law, Dalton and Avogadro's theory of compound elements and reaction stoichiometry, Faraday's realization that atoms carry electric charges, and Maxwell, Clausius, Boltzmann and Gibbs's effort towards an atomic, molecular energetic perspective of the thermal properties of materials. In the 17th century, Robert Boyle realized that the gas pressure under isothermal condition has an inverse relationship with the volume, which led to Boyle's law as indicated here. Boyle's law manifests the first experimental evidence supporting an atomistic theory of matter. It led Bernoulli about 100 years later to formulate a first atomistic hypothesis of gases. In 1845, John Waterston explained Boyle's law by visualizing particles to collide with the vessel wall, exerting thereby forces that results in an internal pressure. In the 18th century, fluid experiments led Bernoulli and Euler to hypothesize about the nature of gases. Thereby, Bernoulli found it necessary to introduce a particle perspective to explain Boyle's law. Bernoulli hypothesized that, first, the pressure increase with temperature is attributed to increased particle motion, and second, the pressure-temperature ratio is inversely proportional to the volume. Bernoulli's first statement, combined with material specificity, made him introduce a particle density given as the ratio between the number of particles n and the volume v. This led to Bernoulli-Boyle's law, as shown here. Note the resemblance with the ideal gas law, which took another 100 to 150 years to find acceptance. Both Avogadro and Dalton recognized the well-defined integer ratios in reactions of compounds. For instance, for ammonia from reacting nitrogen with hydrogen with a 1 to 3 to 2 stoichiometry, or for water from reacting hydrogen with oxygen, exhibiting a 2:1:2 stoichiometry. Avogadro formulated the famous law that equal volumes of gases at the same temperature and pressure contain the same number of molecules, regardless of their chemical nature and physical properties. For a mole of substance, that number is 6 × 10⁻23, known as the Avogadro number. At the dawn of the 19th century, the time was ripe to formulate a truly atomistic theory of matter. The wealth of the accumulated experimental work of former and contemporary scientists and the widely discussed particle hypothesis of gases brought Dalton to verbalize his famous theory. It states, elements are made of extremely small particles called atoms. Atoms of a given element are identical in size, mass, and other properties, or atoms of different elements, different size, mass, and other properties. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements combine in simple whole number ratios to form chemical compounds. In chemical reactions, atoms are combined, separated, or rearranged. The introduction of compounds composed of a limited number of atoms was a fundamental step forward. It addressed a particular shortcoming of the Greeks' atomistic hypothesis. The ancient Greek model required an infinite assortment of atoms to make up the vast material diversity we find on Earth. While Dalton's atom-based composition model of matter was highly celebrated, it bared a significant shortcoming with its assumption of solid, indestructible atom elements. The conundrum he and his contemporaries have been stuck in for nearly half a century is here nicely depicted with Descartes' naive Hooke model. The intent of the Hookes was to mimic atom-atom interactions. The true nature of the interaction or interactions are still escaping the scientists at this time. In our ongoing exploration on what makes nano tick, we will see that we have to pay close attention to assumptions made regarding interactions and their length scales over which they act. And in addition, we have to pay attention to collective phenomena. Towards the end of the 19th century, great effort was put into deriving a particle description of the thermodynamic properties of gases. The fundamental laws of mechanics were applied to atoms and molecules, assigning them kinetic and potential energies. Probability laws named after Boltzmann and Maxwell were employed to describe the average behavior of these vast many-body systems. With it, a new theory was born, the statistical thermodynamics. While statistical mechanics provides fundamental insight into the equilibrium properties of thermodynamic systems, it also describes processes such as the rate at which particles condensation occurs, or atoms and molecules react to form a chemical product, and the collective phenomena that results in distinct molecular arrangements and structures. It is important to note that statistical mechanics heavily relies on the insight of the potentials involved within which the atoms and molecules interact. This aspect requires more insight into the electronic properties of the atom, the molecule, and the condensed phases, and is provided by quantum theories. With the discovery of the substructure of the atom, that is, the electron and the positively charged core nucleus, and the consequential establishment of the quantum theories, the framework was established within which atoms and molecules interact. We will discuss the electronic substructure of the atom and their implications in the next section of this lecture. This brings us to the end of this part. We commenced with the logical perceived idea of the atom some 2.5 millennia ago, until experimentally supported evidence appeared in the last few centuries, leading Dalton, Boltzmann and their contemporaries to adopt an atomistic theory of matter. With statistical mechanics, a particle theory evolved that was well suited to describe large systems that are close to equilibrium. Once we will discuss the nanoscale, we will have to revisit the concept of equilibrium and how the size plays a role. But first, we will continue our story and focus on the atom. It turns out that its electronic structure has tremendous effect on nano-sized particles.